screen.
Never mind.
I thought it was pretty clear.
I'm looking at it. I did it this past time, but now I need to.
Sure.
You know that I could beat somebody, yeah.
He's absolutely right. Yeah, you're right. I know we, yeah, I think there's one other. Yeah, I couldn't think of a word that was there. I was like, maybe we did it. Yeah, I was. I was like, well, I don't want to do it. Maybe. I was thinking, I was like, whatever. I'm gonna run out of like graphics.
Alright, so the homework I just handed back for clarification is actually it's out of 40 points. I know it was marked out of 35 initially online, but that was just a miscount on the number of questions by yours truly. For the most part, people did pretty well. Seems like there were some slip-ups when it came to the basic calc stuff, the Taylor series, and then dimensional homogeneity. You know, checking the dimensions of assorted unit or assorted variables. So those are, you know, remember you've got something that looks like. So someone tells you to find a first order Taylor series here. It's simply a line that is tangent to that point, right? First order Taylor series means a line. First order y equals mx plus b touches that point. It's a second order Taylor series. It's a parabola. It's a third order Taylor series. It's going to be a cubic curve. And then for dimensions, things like mass, length, time, just carry it through, you know, laboriously through. If someone tells you, well, give me mass to the 4th times mass to the -4th time to the -3rd, length to the 18th, and I don't know, length time both -2. Just go through the process of writing the entire thing out in a fractional form and cancel it. Right? It's going to save you little mistakes. So mass to the 4th. Mass to the 4th time -3, or second time to 3, length 18th, length squared time squared, and just start canceling manually, right? So, anyway, remember that there's another homework online, number 3. Let's see if everyone got homework 2 here. Homework number 3 is online. That will be due Wednesday. We'll get back to the Wednesday submission. And let's go ahead and move on to today's material. So, that is the wrong note. So I guess first, before we get going on this, are there any questions on the last lecture, on the latest homework, anything up to this point? No? Okay, so today's topics are going to be spell, Bernoulli examples, and F equals MA normal to streamlines. So in the last lecture, we covered a lot of stuff actually. We got through streamline kinematics, reviewed all the ideas of streamlines, Eulerian Lagrangian concepts. But the takeaway was that we ended up deriving the famous Bernoulli equation. In a word or in a sentence, anyone remember how what was the major motivating principle we applied to get this? Where we said, let's look at a streamline, let's look at the motion only along the streamline, and ultimately what equation that you've all used in every physics class since you were babies did we apply to get that? Sum of the forces is equal to MA, yeah. It's just an M equals MA with a bunch of cancellations, right? It's also thought of as a conservation of energy idea, where this is kinetic energy, this is gravitational potential energy, and this is pressure potential energy. The idea is that the sum of these is always constant if you stand along a streamline. And this should make sense. Water starts out at the top of a hill, big Z, flows downhill, picks up speed, smaller Z, bigger V, right? You pump up a super soaker, big P, no V. Squeeze the trigger, water comes out, all of a sudden P goes to atmospheric and V gets really big. So these are really, it should be a fairly intuitive equation to use. The more difficult part is using it correctly. So the important one is, remember, it's always a long streamline. Point 2 is that it only applies to steady flow. And point 3 is that it only applies to inviscid flow, or approximately inviscid flow. Note we've got, kinetic, we've got gravity or body forces, got pressure or pressure-induced surface forces, but there's nothing in here involving viscosity. So if you're trying to apply this to molasses, it's going to give you a really bogus result, because it's pretty viscosity is a pretty dominant force in thick viscous fluids. So as I just said, remember these, drill them into your minds, that to apply this you have to follow these 3 tenets. Now remember also, here we go. So remember, when we're talking about streamlines and steady flow, right? So, points 1 and 2 here sort of work to your advantage, because when it is steady, streamlines, streak lines, path lines are all the same thing. So these smoke traces can be thought of as, even though they're actually streak lines, can be thought of as streamlines. And then you've got, points where you could say points 1 and 2. You can apply Bernoulli between those because they lie along the same path line, and therefore, by inference, lie along the same streak line. There's another way to think about this, and that's, note that every term in here has units of pressure. We've got pressure, we've got rho gz, which works out to units of pressure. This is called dynamic pressure. And so we can start talking about this as a sum of pressures. Dynamic pressure hydrostatic pressure, and simply static pressure, right? If we get rid of the velocity here, if it's no longer a dynamic problem, then we simply have hydrostatic and static. Static being something you would actually measure with a pressure probe, right? And so with this gone, this simply turns into our governing equation of fluid statics. So this allows you to find, the pressure at the bottom of a tank, so on and so forth. If we get rid of this term and assume that everything's happening along a constant elevation, such as the case here, right? If we take this yellow point, we consider this point right here, then what we get is this 1/2 rho v squared plus p. The combination of these two form what we call the stagnation pressure. The reason for this, so let's go ahead and apply the Bernoulli equation just quickly in our heads along the streamline, right? Well, we know they're at the same elevation, right? So we can cancel the z's out from both sides. So we've got as 1/2 rho v1 squared plus p1 equals 1/2 rho v2 squared plus p2. Velocity to stagnation point is 0 by definition. So that means that over here at point 2, all we've got is our p. Upstream it's p1 plus 1/2 rho v1 squared. So 1/2 rho v squared plus p is equal to the pressure at a stagnation point along that streamline. So that's why these two terms grouped together are called the stagnation pressure. This is, there are a ton of different ways of breaking down the Bernoulli equation. There are ways where they turn it into a more formally an energy conservation law. You can multiply and divide by rho and to get it in terms of height, as I mentioned before, where you have the dynamic head, the gravitational head, and the hydrostatic head. But ultimately it just becomes multiplying and dividing this thing by constants, right? And different ways of grouping the values together. But it's always helped me a lot to think of it as an energy conservation or pressure conservation problem. Viscosity is left out here more obviously because viscosity is it's a dissipative force. It causes losses via friction, and therefore, what does friction create? You rub your hands together, heat. And heat is a non-recoverable form of energy loss. So if we brought viscosity in this problem, this constant would no longer be constant, right? Because anytime you have fluid flowing past a body or fluid particles flowing past one another with different velocities, you end up with friction. Therefore, thermal losses and your conservation of energy no longer applies. So leaving viscosity out for now, there's nothing to dissipate that energy in a way that it doesn't get recovered in some other form. So that's enough on that for now. I feel like I'm proselytizing to you guys. So let's look at kind of a fun example. Let me see. Actually, first, I guess, I wish I could just put this on the board. Well, we applied it to the hydrostatics problem, remember? Like I just said, if you eliminate the V's, such as in a body at rest here, then you end up with just the fluid statics problem. And what I mentioned before, I guess I was probably a little unclear. No, we don't really have any streamlines going on because the fluid is everywhere 0. But the important thing is that between 1 and 2, we're not crossing any streamlines either because there really aren't any. And so the fact is that if there are no streamlines, then you don't really need to worry about assumption number 1 because it's a statics problem anyway. In the next problem we talked about, the stagnation pressure on this bicyclist's nose. And the big takeaway here is that instead of putting your, putting your coordinate system fixed like so, right, you should actually put the coordinate system somewhere on the bicyclist moving with his velocity. And the reason is, if you're an observer at this point, or at this point, as the bicyclist goes by, you're going to see the spike in velocity as he goes by. It's going to be an unsteady problem, so you're violating the steady flow assumption. However, if the coordinate system is moving at a steady velocity with the bicyclist, the flow is coming in at a steady rate, everything about the cyclist and his conditions appeared in the same spot at every time in this local coordinate system, it's a steady problem. We're assuming this streamline here connects with his face, so we're along the same streamline, and it's air, so we tend to ignore viscosity, so equation 3 is assumption 3 is satisfied. So, we're able to cancel these out because they're at the same elevation. V2 in this local coordinate system goes to 0, and so we can see that we have the stagnation pressure where P2 is once again equal to just P1 plus 1/2 rho v squared. So let's get a little less formal with it for a second. You've probably seen this trick before, right? Where someone takes a jet of air, ping pong ball, and floats it on top. I've seen people do it as a party trick where they blow into the air and the little ping pong ball stays magically locked in the stream of air, right? Question. Do you think Bernoulli's equation has anything to do with this? In fact, asking that question in class should probably be a leading fact. The answer is, surprisingly, yes, it does. So let's consider a really big blown up version of this this nozzle. Let's, blown air out of it. We've got a ping pong ball, right? So we've got streamlines, some stagnating, some all right. Now this is actually kind of a tricky question because you're not supposed to know the answer yet. But what do you think the pressures at 1 and 2? How do you think they compare to one another?
Hovering, right?
It's hovering.
They're the same.
So what?
They're the same.
That's actually, if it's hovering, you've got to have a higher pressure on the bottom, right, to support its own weight. However, if we simply believed Bernoulli and had a completely inviscid assumption, then they would in fact be the same. When we get into potential flow, that is ways of modeling flow that has zero viscosity, then what you start to see is that you end up with streamlines that look like this, and you end up with a mirrored stagnation point here, right? It assumes that somehow there's velocity equal to 0 here, and then a streamline comes off of it. This isn't obviously what happens in real life. Remember I mentioned this is conservation of energy. Well, this is a real world system. So along the edges of the ball here, you're going to have friction, and therefore dissipation of energy to thermal losses. And so what you end up being unable to do is maintain all of the total energy or all the total pressure that you originally had at the streamlines here. And what that causes to happen is you get, a buildup of pressure here as it stagnates and it slows down. The velocities here are at a maximum, and so the pressure gets really small on the sides. And then as you start to come around here, it's unable to recover the same amount of pressure it had here. So the pressure up here has to be smaller because some of this total energy has been lost to viscous dissipation. So you end up with P1 is smaller than P2, which is why it floats, right? We'll get into it more later, but there's also the fact that because the pressure is unable to recover its original value, you end up with flow separation off the back of the ball. So the streamlines don't actually stay stuck the whole way around. They end up forming this sort of eddying, what's called base flow behind the ball, but more on that later. For now, hopefully that's kind of a qualitative notion of why the ball is floating in place. The next question is, what happens if we apply a force to the side of the ball here, right? So ball. Just to make this a little more straightforward, let's assume that it is right at the edge of the fluid field. All right. Point 3, 0.4. Okay, velocities, 0.3 versus 0.4. Which one do you think is higher? 4, right. That's flowing fluid. And so, by inference, in Bernoulli's equation, where do you think the pressure is smaller? Right, if V4 is greater than V3, then,
Smaller pressures at 3.
well, oh, sorry, this is,
Yeah.
I wrote that, the
That's
sign
okay.
wrong.
Yeah.
There we go.
So
Volume
that's
of 4.
4.
So, right, so P4, therefore, is smaller than P3, which means this thing's going to experience a suction force that pulls it back into the center of the stream of fluid, right? So that's why you get that sort of bouncing back and forth behavior of the ball as it's bouncing up to the edge of the stream and getting pulled back into it, right? So I dug around in my closet to find my shop vac to bring it in and do it in class, but couldn't find a ping pong ball. So, all right. So, yep. So we just covered. It's a case of. Okay. So just covered. Yeah. It's a case of velocity past the side closer to the center of the flow jet being greater, and the pressure therefore pulling it back in. Next topic we're going to talk about. These are called, it's a thing called a stagnation tube. There we go. And all right. So, question here is, we're putting a tube filled with water into a tank of water, right? If it's just a hollow tube, open on both ends, it's in a U shape, put it in the water, it's going to fill up to the level of the water, right? What happens as soon as you start a velocity flowing in the end here, right? The water in the tube is going to rise. The question is, you know, how much does it rise? What's the actual elevation here going to be equal to? So we're going to go ahead and again apply the Bernoulli equation to this problem to figure out where, or to figure out how high, to figure out just exactly how high the water rises. So I'm going to do this again. So first question is, where do we put our points that we're going to evaluate the Bernoulli equation at? Let's say we've got 1A, got 1B, 2A, 2B. All right. What do you think the first point we should evaluate is? If we know we're going to end up applying it between 2A and 2B, right? Because the streamlines here, it's a hydrostatics problem inside of the tube. But is there any reason that we should choose 1A to 2A as our first 2 points to connect with the Bernoulli equation. Would this be a valid choice?
Asking to choose 1A.
I'm asking what, like, between, so if 2A is the point where we're going to try to, is our second point for the Bernoulli equation, right? What should be our first point? 1B, right? Is there any reason we should not choose 1A? Right, it's crossing streamlines. We don't need to, yeah, just shout it out. Plus C1 plus P1 rho B plus rho B plus 2. Alright, so yeah, we've eliminated 1A is a good choice to begin with.
Why do we eliminate 1A?
Because it's because of our streamlines, right? We've got flow velocity coming in this way. Then 1A to 2A crosses streamlines,
Oh, I see.
right? So 1B is along the same streamline as 2A. So we're going to go ahead and make this our point 1 and this our point 2. All right. So any terms that we can cancel right off the bat? Good. Rho G Z out of there. All right. This is obviously moving, so we need our velocity. It probably has some pressure because that's below the free surface, so this doesn't go to 0. What about point 2? What can we assume about point 2? Well, look at the name of the problem right here. Right. So velocity can go to 0. Right. The idea there is because we're assuming this has reached steady state. All right, we've put this tube into the water. We have, turned on this channel, caused the flow to occur, and we're waiting till this fluid rises to a point and then stops. Okay. So if this fluid is stopped, unless it's spouting out the top, then everything in this tube is static. It's holding still. So this becomes a manometer in essence. All right. This is a manometry problem, where the idea is this somehow the height here will tell us the pressure at this point, and the pressure at this point should be our stagnation pressure. Okay, so by masterful manipulation of this extremely difficult problem, we see P2 is equal to P1 plus 1/2 rho V1 squared. Right. All right. So just to keep things clear here, let's go ahead and rename this point 3. Yeah. So we've got now 1/2 rho V2 squared plus rho G Z2 plus P2 is equal to 1/2 rho V3 squared plus rho G Z3 plus P3. All right, terms we can cancel out here. We're now applying from point 2 to point 3. Okay. Velocity, one side, two sides? Oh, yep. Velocity, gone. All right. And then that ends up being about it, right? We've got fluids not moving, but they're at different elevations. We don't know anything about the pressure at those points yet, except that we can make a substitution here, P2, based on the pressure of P1, this being P2 being the stagnation pressure. So what we end up with is P1 plus 1/2 rho V1 squared plus rho G Z2 is equal to P3 plus rho G Z3. Did I get that right? If I'm substituting P2 into there, then we just end up with this equation here. So now if we call this, if Z is measured from the bottom here, so we've got Z2, we've got Z3, and the distance between them we simply call H, right? The height of the column fluid. what we end up with is P3 is equal to P1 plus 1/2 rho V1 squared plus rho G, sorry, minus rho G H. Now, all right, what do we know about the pressure at 3, actually? Got ahead of myself here. What's above it? Yeah, exactly. Atmospheric. So now we can go ahead and say P atmospheric. So if we're worried about gauge pressure, we can go ahead and we can go ahead and get rid of that, right? But we won't do that quite yet. We're going to go ahead and say our goal here is to solve for H, right? How high does the water in the tube rise? So we've got H now. We'll say rho GH is equal to P1 minus P atmospheric plus 1/2 rho V1 squared and then dividing through by rho G, we end up with P1 minus P ATM over rho G plus V1 squared over 2G. So here's our solution. Why is this useful? Right? The idea here is you can take a tool, a stagnation tube like this, and stick it into a flow, and if you know the pressure at this point, there's lots of ways you can get it. Right? In some cases, if you can assume that the streamlines are all the same, then there are ways you can show that it's simply hydrostatic pressure. But anyway, regardless, let's say that you're measuring the flow in air, and you have some fluid of another density here. The idea is you can, by assuming that the pressure is atmospheric everywhere, that is, pressure gradients are small, then you simply boil this down to a problem of the velocity and gravity, and in some cases the density of the fluid in the tube. So again, why is this useful? Well, it allows us a direct pressure, a measurement of the square of the velocity as a function of the height of the fluid in here. Right? As the velocity speeds up, the height is going to increase proportionally to the square of that velocity increase. So they use things like this on airplanes, and flow measurement in pipes. I've had an old speedboat as a kid that I was restoring that had this tube sticking out the bottom, and I was like, oh gee, what's that? It seems like a pretty stupid place to put a hole in the boat. But I traced it back and found it connected to this Bourdon gauge behind the speedometer on the boat, right? And that's how it measured the forward speed of the boat. This is the stagnation pressure at the bottom. Of course, anytime you went up a wave and hit the water, this thing had rocketed and told you were going 120 knots, but that's not in my plywood beauty anymore. All right, next question. Do you think that... Do you think the orientation of the tube matters? That means its rotation in and out of the board. Okay. What's an example where it would matter? Tell me a sort of a limiting case.
So, when these things in and out of the board, the velocity still going this way.
Right. Perfect. Exactly. And in that case, what are you actually going to be measuring at that point? The only pressure that's acting on that point, right, is going to be, the velocity stays the same, the elevation stays the same, and so all the terms in here remain constant. And so the only thing, right, even so on this side you've got a velocity, on this side you've got none. So all that's going to be acting is now you're going to be measuring the static pressure inside the tube. So exactly. So the orientation of the tube does in fact matter. And we actually went through all of this already. Okay. So this leads into the next topic of pitot tubes. And pitot tubes are pretty cool because they sort of combine all of these notions that we just talked about into one instrument. Right? The idea of the pitot tube is now you have a stagnation tube, just like we mentioned, and then somehow you have another tube. In this case, if you can imagine this is a slice taken through a circular pipe, right? And so you have holes kind of going around the circumference of that pipe where they're perpendicular to the streamlines. So at point 1, you're measuring stagnation pressure. At point 2, you're simply measuring the static pressure. And then you connect a differential pressure measurement between them, or a manometer, or some way of measuring the difference in pressure between 2 points. And then what you end up getting is that the velocity, if you go through the same process we've been following, the velocity can be written as a function of the square root of the difference between pressure at 1 and pressure at 2. And then by applying hydrostatics, you show that at 2 equal points here, the pressure difference here will be equal to the pressure difference here. And so by connecting a differential pressure measurement tool, such as a manometer or a diaphragm gauge like this, you can measure the velocity directly. You don't need to know anything about the actual free stream pressure. So stagnation tubes on their own are cool, they're nice, but you need to know the upstream pressure. And the way you do that is by adding another set of holes, measuring pressure at another location, comparing them. So, it was sort of a half-truth when I said that stagnation tubes are used on planes, submarines, and such for measuring speed. More realistically, they use pitot tubes. So if you've ever been loading onto a plane and you see these little L-shaped tubes sticking out of the fuselage, if you haven't, take a look next time if you're boarding a plane. Go ahead and look down kind of underneath the cockpit, and there are going to be these little L-shaped tubes sticking forward. Those are their, speedometers essentially, or they're pitot tubes that they use to measure the airspeed. Okay. So we've already gone through that. Pitot tube applications. Huh?
Can you go back, please?
Yeah. Any questions on this stuff? Okay, good. All right, so we just talked about pitot tube applications. These are these little L-shaped tubes I'm talking about sticking out of the fuselage on airplanes. And you'll see these all over the place. That's on a really small little turboprop. But they also use these on giant jetliners and such. Okay, the next question is just sort of another way of playing with Bernoulli equation, where that's all we're doing today, really, is playing with Bernoulli equation. I don't think we're going to end up getting to F equals ma normal to streamlines until Monday, but that's fine. So what happens if we talk about a fluid that is dropping through space, but the pressure stays the same, right? An example would be, let's start this slide over. So like this soda bottle here has some holes punched in it, right? These constitute streamlines, right? The fluid sticking to them. And it should be atmospheric pressure everywhere, right? Because it's exposed to the atmosphere. But as it's dropping in space, you end up trading out gravitational potential energy for kinetic energy. Just like, the problem where somebody says if you throw a baseball at this trajectory this fast, this high, how fast will it be going when it hits your little sister, right? That's the, sorry. They never hit my sister with a baseball, I promise. And so you end up with the same sort of equation of kinematics, right? Torricelli's equation, which tells you that the velocity is simply equal to some function of the distance dropped by those fluid particles. Same thing applies to streamlines. And so, once again, if you're looking at sort of the trajectories of all the particles, they describe these parabolic paths, which is exactly particle motion. Same laws of physics, only now it's being applied to streamlines instead of individual fluid particles, right? Okay. So, that, ignore this. This is a holdover from the slides coming from a Mac. So again, we're assuming pressure is everywhere atmospheric on all these streamlines. So the only thing that happens is the velocity is going to change and the elevation is going to change. Again, going through, solving for the velocity at some point below where it started, you end up with this 2gh plus the starting velocity. In the case of, I keep coming back to this, that soda bottle here, the velocity right before it jumps out this hole is going to be what? 0, right? Approximately 0. So we can cancel this out, call this h, and recover the torsion of this equation. Okay, this one's a little bit more complicated. This is one that we're going to spend a few minutes on because I put a slightly more complicated version of this one on the homework, and so I'm going to cover it now. You're going to have to read about it. Now, there's a problem with confined flow. This involves using Bernoulli's equation to sort of come up with a system of equations that tells us how fast water's flowing out versus how fast it's flowing in based on the size of the tank that we punched a hole in the bottom. All right? So, if you've got your keg of beer and, I don't know, Joe's drinking it out the bottom, some rate, right, through a tap, some diameter. How fast do we need other Joe dumping beer in the top to keep us flush, you know? So that becomes a conservation of mass problem, right? Mass in, coming at the top, has to equal to mass out, and at the bottom. Which means the mass in is going to be equal to the velocity of the, sort of the velocity of the inlet times the area of the inlet, right? And the out is going to be the area of this outlet times the flow velocity through the outlet. All times rho. Alright, so you end up with this rho A1 times the velocity at 1 equals rho 2 times this area here times velocity at 2. So now let's go ahead and start with this one because this one's pretty straightforward. So it says this has a diameter of 0.1 meters, 10 centimeters. That means A2 is going to be equal to pi times little d squared over 4, alright? So, now the area at 1, and this is probably going to prompt some questions. Do you think, let's go ahead and talk about the area of the tank here, right? The actual top of the tank. Now, we're going to call this the entire inlet to the system. The question that we have to ask is, well, how do we use a velocity at the inlet, right? If we're assuming this is steady state and the water level remains constant, then what are we even talking about? Like, this equation starts to not make so much sense. The thing to remember here is if we're talking about an open tank, and we're dumping a bunch of water in, you know, this initial group of fluid particles, as water is removed out the bottom, is going to start to move downward, right? So the simple way to think about this is that the rate at which each little previous free surface migrates down the tank is RV1. And they're simply being replaced on top by more water coming out of this pipe. Okay, so that's that. I just want to point that out before we get into this. So Now the area at 1 then is going to be equal to pi times big D squared over 4. And so let's go ahead and first, plug these guys into this conservation of mass, right? So we've got rho V1A1 equals rho V2A2. We're talking about the same fluid at points 1 and 2, right? We're not assuming anything's changed, so we can go ahead and cancel rho off both sides, which simply means that V1 A1 is equal to V2 times A2. Should be pretty simple. Volumetric flow rate in equals volumetric flow rate out. So let's go ahead and solve for V2. I think it's V2 first. As a function of V1. There we go. Alright, so we end up with, well, we'll leave this here for now. So this is equation 1, right? We've got essentially two unknowns here, right? We've got V1 and V2. We don't know what either of those are. So we have one equation now, two unknowns, so we need another equation. And that's going to come from Bernoulli. So we've got points. One and 2. So we've got P1 plus 1/2 rho V1 squared plus rho GZ1 is going to be equal to pressure at 2 plus 1/2 rho V2 squared plus rho GZ2. Alright, anything that you can see we can cancel out on point 1. Or between point 1 and point 2, anything that remains constant. B, right? Well, the density doesn't appear in all of our, not yet at least, but it will, because somebody pointed out the pressure at both these points is exposed to the atmosphere. So equilibrium says that pressure at both these points is atmospheric, so we can drop it from both sides. Now, every term left has density in it, so we can go ahead and cancel density out. So we end up with V1 squared over 2 plus GZ1 is equal to V2 squared over 2 plus GZ2. Alright, so here's our second equation. We've got equation 1, equation 2. Came from different principles, two equations with two unknowns, V1 and V2. So now we need to solve for, or we need to combine these together and go ahead and solve for a V. And we don't have a whole lot of time left. Let's see if we can get through this. Alright. So, let's go ahead and solve for V1 using this. This is going to give us V1 is equal to V2 A2 over A1, right? Plugging in A2 and A1 as the diameter, or the areas of these circular inlets and outlets, we end up with V1 is equal to V2 times little d over big D squared. Let's take this equation for V1, go ahead and plug it into this formula over here. And what we end up with when we do that is, I'll go ahead and save, I need to, so when we go ahead and do that, we end up with V2 d over d squared over 2 squared plus GZ1 is equal to V2 squared over 2 plus GZ2. Alright, if we go ahead and we subtract this GZ1, GZ2, or GZ2 from both sides, we can go ahead and write this V2 squared times d over d to the 4th over 2 plus GH is equal to V2 squared over 2. If we multiply both sides by 2, we end up with a 2 there. If we factor out this, we solve for V2, solve this equation for V2, what we end up with is going to be V2 is equal to the square root of 2GH over 1 minus D over D to the 4th. Okay, so we've got V2, this whole thing. So we've got V2, we've got A2, so we can plug this back into our V1A1 equals V2A2, right? We can calculate then V1, and because Q, or the rate of flow into the tank here, right, the volumetric flow rate into the tank is simply equal to both of these. In other words, I don't remember who I designated our class drinker. We'll go ahead and say Grant this time is got to consume, or has got to dump in Q liters per second or whatever unit system is of beer into the keg to keep Michaela from running dry as she chugs it out the bottom, right? So hopefully that should be fairly straightforward. I think we're about out of time. But are there any questions on this problem or any of the other samples in class? Cool. Alright, there are office hours for an hour after this. And otherwise, we'll see you guys on Monday. Have a good weekend.
It's not just a birthday.
He likes to just throw it in there and he puts it already.
No one has
I do not have my leg together. There was, I didn't go. Yeah, cause some people don't know. Yeah. No, they were like.
Could have added up front, but I think you're gonna
No, it was. I just.
Mine got added up wrong as well.
Okay.
What is
Let's see.
Yeah, I think so too.
There's some more math errors. Tell you what, I will go and just retotal these and update the grades on Canvas accordingly. And you're right, get these back on Monday.
Thank you.
Alright.
We also are not going to be here for the first exam. They have like a drill comp for the Navy this So I wonder if it's possible to either take it earlier, like on Wednesday, or after.
Yeah, so the dates for the conference, or for the exam are definitely, can still take place around. Short answer is yes. Either I will move it by a day or two for class, or I can, have you guys take it.
I could take it on the Thursday, but I don't think you will be here on the Thursday.
Yeah, I leave on Thursday, I leave the day before.
Okay, let me pull it.
I would just.
Especially in companies. We have to start.
There's like an hour of it like updating and restarting.
Yeah, see, that's why I haven't updated to Windows 10.
So, yes, I have it written down for October 7th.
Enabling one use of the options. You can't do that with
Yeah.
in 10, it just does it automatically. And, it's not.